Good afternoon, everyone. I think we can start. So I'm Parisa Korjamshidi, chairing this session. So this session is best paper presentations. The first one is gaining insight into brain damage and rehabilitation through digital twins. This is presented by Risto Mikolainen, if I pronounce correctly. They are here. Okay, perfect, please.
Okay, so this is about digital twins, indeed, and it is a collaboration of two different disciplines. I'm representing computational science and AI, and my colleague Swati Kiran from Boston University is a neuroscientist, and she's actually right there from Boston University, and Boston has a booth in the back there. So we've been collaborating for several years, and it's been really interesting to see how what originally seems like a really pie in the sky, bringing computation into neuroscience, is now actually reality, and that's what I'm going to talk about. So this is what we're up against. People who've had a stroke, there's a serious impairment in their language ability at first, say 3 months, and then they recover, and if we treat them well, they might recover quite well, depending on a patient and their background. So let's just hear some of these patients, or one patient in particular, first at 3 months and then 12 months, and see what is possible. So they are asked to name objects, and at first they have real trouble doing that. Let's see if we can hear that.
It's for it's sunny for light.
Yeah, it starts with k.
It's a couple. I can't get the word. A stork for a fab.
So this one starts with k.
Color. It's a stork. It's stork. A stork. A stork. A snort. It's a stork.
Okay.
So this one starts with k.
I think you can get the idea. It's very difficult for these patients to find the words, and they keep coming back to the same kind of sounds. They go around it, and this is 3 months after the stroke. They have real trouble finding words. This is at 12 months, same patient, and you can see remarkable improvement here.
A candle, a clown, a kite.
Yeah, this is what we want. We want to be able to allow them to recover as fast and as completely as possible, and the treatment makes a big difference. So the goal is to be able to use AI and to evaluate a variety of treatments and then find which ones really work well for a particular patient. And this is crucial. Patients are all different. They have different language histories, they have different impairments, the stroke may be different, and they recover at different rates. So what we really need is a system to predict how the treatment will work so that we can pick the best one. Now, a big challenge is that this is not your usual machine learning problem. We don't have millions of examples. We have a few patients, we may be able to characterize them, but there will never be enough data to train a typical machine learning system. So the standard machine learning methods will not work. But instead, we have to use another kind of architecture. And even though today LLMs and deep learning is all the rage, there are other architectures that people have developed. In particular, architectures that are more informed by neuroscience. You start with an architecture that already has structure from neuroscience, and then all you need to do is fit that architecture to the particular patient, their performance, their damage, their recovery rates. So, of course, it's a big problem, and we're just barely starting. So we are looking at one domain, naming, in bilingual patients, Spanish-English bilinguals. And the treatment is simply to select whether to treat these patients in English or in Spanish. So one-bit decision. Now, there are no current guidelines in how to select that language, which means that whatever we do, we can do worse than the current state of the art. So that's a really good application for this. We can hope to do better. Okay, so the model is called PILEX, and it's based on some work that's been around for a while on how the lexical system is organized. There's a semantic store, and then there are different languages in different areas that incorporate Spanish and English words. So the idea is that we have semantic representations. They are vectors of semantic values, and they are given to the self-organizing map. That's the architecture, self-organizing map, a neural network that's laid out in 2D so that it's a map of words. In this case, semantics on top, and the two languages on the bottom. So what the words mean is in one map, and what the words sound like are in those two maps in Spanish and English. So this structured representation starts from a brain theory, and then we implement it so that we can fit it to a particular patient. Now we have three tasks. First, we have to model a patient before the stroke. And that means their age of acquisition of the second language, how much of each language they actually experienced over their lifetime, and how good they possibly were in both languages before the stroke. And then the stroke happens. We want to model the damage, how much of the semantics they've lost, how much of the naming performance in both languages they lost. And the last step is to model the effects of treatments. There is some spontaneous recovery, but we will also incorporate those treatments, training of different kinds of words in Spanish and English in order to evaluate how well the treatment works. The first step is this is showing a history of the different languages. So there's Spanish first and up to age 20, and then a considerable amount of English since then, but Spanish still keeps going. So that's a profile of one patient. Here might be another one. All Spanish at the very early age, but then mostly English. And this patient has very little English altogether. So these are different language histories, and that determines much of their language recovery patterns as well as damage. So that's the first step. We can do this with questionnaires, ask their caregivers, ask their history, and we get some rough approximation of how well they know those two languages. Now, this is something very detailed and technical in a sense. This is a map visualization. So if you have a semantic map, there your words that represent similar meanings are nearby. Animals, vehicles, things like that might be nearby on the map. This is actually phonetic maps. This is what the words sound like. And here you have areas for mostly short words and medium length and then very long words, because that's the main characteristics of what the words sound like. And what you want in the map is that you want it to be regular, like this one on top left. I mean, there are large areas and they are uniform, they are consistent. It's a well-organized map of what the words sound like. And that was a simulation of a patient that has early second language acquisition and high exposure. So this is the second language map. It looks good. If you have early second language acquisition and even low exposure, you still have a pretty good map. But then when you have a late second language acquisition, it starts to get a little bit messier. You see that the areas are broken up. There are areas of the map that don't have any representations, and late and low is even worse. So this way we can model individual patients and what their competency in one language is or in the other. The map structure is actually fit to the patient. Now here's a movie that shows how those maps organize. We were looking at the second language map, which is an early acquisition but low exposure, so it organizes very slowly. The Spanish map organizes much quicker. And here again, the colors indicate the types of words, what they sound like. And you see that we get ordered maps. This one is not as good as the Spanish map. Just an illustration of the computational model of that individual patient. Okay. So that was the first part, modeling the patient. The second one is the damage. And here we have some choices. I mean, we can model damage that's very focused. I mean, it's stroke, so it is often damaging a local area of the map. Or it could be something more noisy, but still relatively focused. We also have a choice of where the damage occurs. It turns out that the most relevant part is the semantic map. You lose some kind of representation of meaning, and that often explains both the semantic impairment as well as the phonetic impairment, the types of words that you cannot say. But in a complex case, there might be also damage in other maps, including this English map here, which means that we have a different, another parameter to fit the patient, a more complex behavior. But that we can do, and then we can fit the behavior of the patient after the stroke. The third modeling challenge is to model the treatment. And here we have quite a few parameters that we can change in order to simulate treatment. So we have 15 treatment words that are used over and over again, very much like what we do with patients in real clinic. And it means it's a naming task. We show a picture of an image to the patient, and here it means we activate a semantic representation and ask the model to say what that word is, what that object is. So it's a naming task that we're using in rehabilitation. But at the same time as we are changing and modifying and recovering these connections from semantic to Spanish, the map itself continues to organize. It continues to recover some of the representations that were lost. The nearby units take on representing those meanings that were lost. Also, there's some spontaneous propagation through the secondary language connections, and that means that the connections between the two languages will also strengthen during this treatment. And also the connections from semantics to the second L2 language. So we have multiple areas of the map that recover when we are doing this treatment computationally. And there's also spontaneous recovery like there is in the real world. The maps are trained on the whole vocabulary a little bit so that they recover on their own outside the treatment as well. Okay, so that's the third model. Now let's put the models to work. And this is most exciting because since the 80s or so, I've been trying to get these models to work so that it would do something useful, cognitive science. It's finally happening. We had these models in a clinical trial, NIH-funded clinical trial for several years, where we obtained a number of patients and then modeled individual patients using this approach. We made models of their language performance in 2 languages, and then tested the different treatments, trained them in English, the models in English, trained the models in Spanish, and found out which one works better. But it was a clinical trial, so we also had to do this randomization so that we can really evaluate whether the treatment helps. And as far as we know, this is the first clinical trial of digital twins of real patients. And I think this is a start of a very interesting new area where we have, in addition to in vitro and in vivo, we have in silico clinical trials. So let's see how that worked. So we start with creating the model of the patient, their language history. We use the large vocabulary to train those maps. And then we have the stroke. We cause this damage, and we fit those possible damaged areas to the naming and semantic scores, pyramids and palm trees. And then we test the 2 different treatment options, whether we treat the patient in English or Spanish. And the model will predict how well the recovery will work out in both cases. And then we compare how much improvement there is in the 2 languages and choose the one that results in better outcome. Now, we can ask, this is what the clinical trial asks. Will the patients who were treated with the model's choice of languages recover better? Okay, here's the bottom line. Not really. If you just summarize the results across all the patients, there is no statistically significant difference on whether you follow the model's predictions or you don't. You do the opposite, because if you had 2 choices, English, Spanish, you could treat them with the model or against the model. So that was a little bit disappointing, you might imagine, but it turned out that if you look closer what happened, you see something really interesting. First step is to cluster the patients into groups according to their language history. Not just how severe their damage is, but what their history is like. And it turns out there were 5 different clusters that we could identify. And now if you look at the results, there's actually real big difference between model opposite and model treated groups. So the solid lines are those that are model prescribed, and the dotted lines are those that are opposite. And we are hoping for a big difference, of course. Now, still, if you look at those who had very mild impairments, it didn't really matter. They would recover anyway. Or if you look at those who were really severe, again, it didn't really matter. It was very difficult to make any progress there. But in the mid-range, there's actually a very significant difference. Like this is predicted, this is actual, and this is if you are treated with the model or against it, there's a big difference. You recover much better when you follow the model's recommendations, the digital twin. Okay, so one size does not fit all. That's what we learned. Not a big surprise, but after the fact, it was actually very interesting that it really matters what group you are in, how your treatment will work. And indeed, we now have a way of coming up with better treatments for those middle severity patients. So that's the conclusion. It's now possible to create digital twins of individual patients. It is dependent on neural network architectures that are not just your standard machine learning, but those that are inspired by biology. So you program in a lot of your knowledge about biology, neuroscience, and then you can do this individual modeling. And it's accurate enough to be in a clinical trial and result in the insight that in some cases, which we can identify, it results in better outcomes. And there's a lot of future work. I mean, we just tested English versus Spanish, but you could try concrete words, abstract words, nouns, verbs. We can try in other impairments. We are now working on dementia patients where the treatment slows down the progression of dementia. And similarly, we can eventually do that in a clinical trial. And the bottom line is that digital twins can lead to better patient outcomes. Okay, thank you.
Any questions? Yes, please.
Thank you for your presentation. Very interesting results. Do you know why the middle ground was the one that was the most effective versus, the upper and lower on that last graph?
Yeah, of course, very important question. But I mean, you can just intuitively understand that if you're really severely damaged, there's less resources that you can bring in and modify in order to recover. And if you're really mildly impaired, even the spontaneous recovery covers most of it. So this is really the sweet spot where the treatment matters. Now, that's really just a hypothesis that's intuitive and logical, but it would have to be verified with more measurements. And one thing we are doing now is to plug this in with MRI data. So actually looking at damage patterns and trying to identify indeed whether there's some signature that would allow us to predict better.
Thank you.
Hello.
Yeah.
Please, yeah.
Thanks for the really great talk. Have you thought of any ways to work with people sort of more globally to try to build models for digital twins? For example, there are neuropsychologists every day in lots of places giving tests, neuropsychological tests. Sometimes they make audio recordings of patients who have aphasia. And so there's a chance of scaling up to thousands and hundreds of thousands of patients who can inform models that you would build to help you build digital twins where you tailor those data to your individual patients. That would require a national effort, but I think maybe it's aspirational for all of us.
Absolutely. This is absolutely true. There is data, it's just really hard to get to. Well, we have a better chance, though, in medicine in some cases, because people are willing to share, but there are political, organizational, national boundaries that are hard to cross. But we can start small. We can start with these data sets that already exist and we can have access to. And we can now maybe separate a couple of those groups. But if you get more data, then we have much more refined groups, and we can have more personalized recommendations on more complex interactions of these variables. So this is definitely the way in the future.
So a small follow-up question. It's one thing to collect data under controlled circumstances where the patient is a sort of wriggling worm under the microscope. It's another thing to collect data of people in a naturalistic environment. So maybe you can listen to them in their homes. We can listen to them in their cars. You can get an idea of the volume of their speech, the cadence of their speech, the prosody, whether they're interacting in a meaningful way with a dyadic partner like a child or a spouse. So the predictions might be different. Maybe people do better in the real world than you might think they do in the clinic. And I'm just wondering what about the naturalistic data?
Yeah, absolutely hard to get though, and hard to measure because the circumstances vary so much. Now, the metrics that we have are pretty standard: Boston naming test, pyramid, and palm trees, indeed done in a laboratory. And there's noise because some people get more nervous, other factors like that. But the real world is a whole another ballgame. I mean, morning, evening, what did you eat? What's the context? I think we are pretty far from being able to collect such data and utilize it because the dimensionality is so high. But, obviously that is a goal in the long term.
Oh, well, thank you for your intriguing talk.
Thank you.
Thank you very much. Let's thank the speaker again.
Yeah, thanks.
Second talk of this session is Synthetic AI Agents for Experimental Social Science. It's presented by Colin Kammerer and colleagues. Yeah.
Thank you very much. I'm really happy to be here. I haven't been thinking about AI deeply for that long, and it's been really amazing to see what people have been doing in fields that are way ahead of us, frankly. So I'm kind of an ambassador from social science, particularly economics and psychology, and I'll talk about some of the controversies and things people are doing now. I have three themes for today. One is AI as a co-scientist, so how can AI help us do better social science, particularly? The second is the social science of AI. So almost every labor economist on the planet, many of whom are super clever, are thinking about the question of how will AI change labor markets? Will there be massive inequality? Do we need subsidies and universal basic income and so on? I'll say just probably a little bit about that just to give you a taste of the kind of things people think. And the last is I'll talk about human-AI interaction, specifically a paper by my PhD student Tom Henning, who's here in the light blue shirt, who I should add is also an author on this project. I'm sorry if I left you out. He was really the driving force on deepfakes. Okay, so this is a kind of graphic from a paper by Matt Jackson and a bunch of others at a conference, including me, which is in review about some different ways that AI can help behavioral sciences. I'm going to focus mostly on the upper left, which is assisted with experimental design, and the middle right, which is simulating participants or so-called synthetic subjects. And analyzing results is something AI has been used, at least in the form of machine learning, in social science for quite a long time. Now it's a very standard technique. Our program requires people to take a machine learning course in CS, even if they're interested in social science, and some other places are catching up to Caltech, which is usually innovative. Okay. So we already use AI to automate tedious tasks that require high conscientiousness, like high quality, and which are often boring, but it's important to do well. So in language, things like Grammarly and Hemingway have been around for a long time. There's a new package by a Caltech alum called Ben Golub called Refine.inc, which kind of pre-referees academic papers for you. That's incredibly successful. Literature review and meta-analysis is extremely tedious. We've worked on a lot of these. I think there's a lot of possibilities to automate meta-analysis. You basically feed a corpus of data, and then you want some AI, fine-tuned AI, to cherry pick out numbers of subjects and statistical p-values and what have you. I haven't seen any knockout results yet, but I think that's a very promising use case. Reproducibility, I'll say in a minute, we're not quite there yet. And ML has certainly accelerated inference from large data sets, although there really are no large data sets that are nearly as big as most of the ones you've heard about yet. But some successes include neurosynth, which synthesizes a few thousand papers doing human brain imaging. Geospatial data is coming along amazingly well, and digitization of humanities and history has been an incredible thing. So now people look at, historical data sets going back hundreds of years in a way that we could not have done until recently. Okay, on co-science, this is just one empirical example of where reproducibility is not aided very much by AI today. But I regard all of these results I'm going to show you as kind of lower bounds, and there's room for improvement, and there will be improvement. I'm confident of it. And so Abel Brodeur, who has been doing a lot of studies of reproducibility, did this paper. So reproducibility here means something very narrow and simple, which is you take somebody else's data and code and see if you can run it, and if are there mistakes, or can you reproduce the tables and figures in their paper? And the reason we do this is the answer is not always yes. Okay, so there often are some small mistakes in reproducibility. So Abel does this in a kind of big teams. And so in this last paper, what they looked at was the amount of minutes it took to reproduce the results. And the cumulative density is just the percentage of people needing 100 minutes or 200 or more. And you can see the human-only profile is about 90% of the groups finish in about 120 minutes. And the AI-assisted, which means humans are using AI to help them, is a little bit faster. And the AI in its own is not very good. So AI assist has a smallish value here. But again, this is the first study to ever do this. Things will only get better. Okay, so in the case of AI coscience in the form of synthetic subjects, so the idea here is to use LLMs as, instead of human subjects, we're asking them questions about what they plan to do or who they want to vote for or how would they trade in a bargaining game. Instead of asking humans, we're going to ask LLMs. And I'm going to talk about three questions, which is, why would we want to do this? Can we actually do it with some success? And when we don't have success, can we do it better? What does the improvement rate look like? This is a graphic from Anthos, which is a really nice paper, as you can see from the title, arguing that social simulations are a promising research method, and I agree with every word in their paper. It's really very good. Okay, so can we do these things? Yes. So this is a panoply of papers that, as the title suggests, are generally suggested that it's very promising to use so-called Homo silicus instead of actual humans. Typically what that means is when we have actual human data, the LMs can be off the shelf or can be steered to act human-like in a wide variety of domains, particularly political science, economics, you can see roughly from the titles, even perceptual analysis. At the same time, there's a lot of pushback from people saying, no, we haven't really succeeded. So for example, the central title in the bottom of the center says, large language models do not simulate human psychology. And typically, the papers on the last slide, the papers on this slide, are kind of butting heads, I think in a pretty healthy way, right? Competition is good, as long as evidence adjudicates debates, rather than just fireworks and snark. Okay, so why would we want to not use human subjects? I've worked with human subjects about 40 years, using a variety of methods, sometimes just having them make simple choices, sometimes they're in a simulated market trading an artificial good, sometimes we're scanning their brains, sometimes we're causing disruptions using transcranial magnetic stimulation, sometimes the subjects are chimpanzees, and I love working with human subjects, but it can be hard work. At Caltech, we're very subject constrained. There's only 1,000 undergraduates. They're very, very unusual non-random subjects, right? So when we study Caltech subjects, we don't do it because we think they're a random sample of humans. It's because they're actually extraordinary, like mathematical skill is very good. And so if they exhibit a certain pattern, that establishes a bound, we can learn whether something's likely to occur in more average folks. We have to get IRB approval to work with human subjects. They cost money because we like to pay them for performance. That's a way of getting better signal, better quality data, because they're paying more attention. They get tired. Over longitudinal studies, like if you want to do things every week for a month to look at medium-run training, they can drop out. It's expensive to replicate, sometimes almost impossible to do the same exact experiment again. And AI subjects have none of these problems. Okay, here's an example of can we do this successfully, number one. This is a paper that uses 70 social science experiments on an online platform called TESS, TESS. In those 70 papers, there's 476 effects. So usually that means there's a treatment, like you ask a question one way versus a control, and we're understanding the effect of the treatment on human subjects. Okay, and this is just a cartoon from Hewitt and Asher Kumar showing the pipeline of what they're trying to do. Okay, so on the left you see a scatter plot. The x-axis is the GPT predicted treatment effect, and the y-axis is the randomized controlled trial, RCT treatment effect. The accuracy is really good. The R-squared is 0.9, and if you notice the upper left is where GPT thinks the effect will be negative, and the RCT was actually positive. This is where GPT says positive, it was actually negative. There's very few points in those off diagonals. Right, so they're generally predicting the sign very, very accurately. Not only that, if you look on the right, the progress from generations of GPT is amazing. It starts out worthless, it's 0. And by the end, it's around 0.91. That's the graph you see on the left. And part of that is that these effects were kind of predictable. So if you ask human subjects who haven't read the papers, you know, what do you think the effect will be? They're actually pretty accurate too, 0.82. But the point is that GPT goes from worthless to almost perfect in a very short amount of time. So that's a win. Okay, number 2, stock market bubbles. This is something we're working on with Tom Henning. So this is a graphic of 4 famous stock market bubbles. These are really huge effects. Basically, the price goes up by 80% and then down by 80%. These are scaled so that 0 is the day of the peak. So all the peaks are scaled at 0, okay? And the bubbles are really dramatic. Okay, so in order to study these, we did some human subject experiments a few years ago, published in AIAS. And on the left is data we collected from a paradigm in which we create an artificial asset. We give them some experimental currency that's going to be converted to money at the end. You can use the currency to buy stocks, and they pay a financial dividend that's converted to money, or you can invest in bonds that yield 5%. And the design is set up so that if they're pricing rationally, they're equalizing returns from holding stocks and returns from holding bonds. That generates what's called an equilibrium price. In this case, it's 14. But the price they actually trade at is whatever they as a group decide. There's no deception, there's no confederates. They just decide what price to trade with each other. And as you can see, there are typically bubbles. The black is the average of all these. The bubbles vary a lot in magnitude. There's a few like this light blue which are not very bubbly. The price is 18 or 19, but the median is quite high. The bubble is about 3 times as high as the fundamental. On the right is a replication of this. The left one has 50 periods of trading, and then you trade in your stocks for a fixed amount of money that they know. The right is 30 periods of trading, and so what we're going to now do is ask various LLMs how they trade in these markets. This is plain vanilla baseline. We just give them the human instructions to say, how would you trade? And the answer is, they don't look very human. So the human prices are on the right. It's the same data you just saw, but the scaling is different. You can see it goes up and down. And none of these markets reliably produce, this is just 3 runs each, reliably produce human-like bubbles. Grok 2 and Mistral are not too bad, but Mistral, for example, overshoots, which the humans never do, and a number of them just give essentially the textbook answer, which is I would trade at 14 because that equilibrates some numbers. So they're not exhibiting this kind of human irrational exuberance, if you will. The next step in our program, probably many of you are thinking, is we're going to try to steer these models and see if we can produce human-like behavior. And if we can do that, we can then use them as humans to make all kinds of extrapolations and see what happens. Can we do better? So this is a cautionary tale. I think it's quite interesting. So in this game, it's called the number game. This is not a complicated thing, but that's good for a talk like this. You can get it across quite easily. 2 people choose an integer 11 to 20, and there's 2 simple rules. You earn the number you chose, so picking a high number earns you more money, and if you get a bonus of 20, if you pick exactly 1 less than the other person. So you want to pick a high number, but a little less than the other, right? And you might think this unravels, so I want to pick 19 and 18, but it's not that simple. And in fact, this is a graphic from Ben Manning, who's Gen Z. As you can see, this is what we call level 0. Oops, sorry. This is what we call level 0 on the left. Somebody says, wow, 20 is the biggest, I'll pick 20. And that's a behavior that you see in the data, but also it then forms a belief in this cognitive hierarchy theory that is used by level 1. So a level 1 player might say, I think people will pick 20, so I'll pick 19. So I can be one below. But of course, you can iterate that path of reasoning. So this person picks 19 in the middle, and then the hooded wizard says, gee, if they're going to pick 19, I'll pick 18. But wait, what prevents them from picking 18? I'll pick 17. And it turns out in this game, if you go down to 11, nobody gets the bonus. So in fact, the equilibrium, that is the set of behaviors, which is the best response to other people behaving in that way, the so-called mixed Nash equilibrium, is to choose somewhat randomly from about half of the numbers, 15 and up. Okay. So this is the first paper on this that just came out in June. So the human data is on the top. You can see people mostly choose higher numbers, 16, 17. The Nash equilibrium is that graph in the second panel, right? So the humans are not too close to the equilibrium. They're kind of moving in the direction of the equilibrium down from 20, but not closely. And the GPT models are terrible. So the title of the paper was, Take Caution in Using LLMs. And you can see the publication date, well, maybe you can't see, but I can, June 13, 2025. SpongeBob voice. So Ben Manning and John Horton read this paper and said, you know, we can steer this, or we can try to steer this to do much better and make it more human-like. And so what they did was they used various prompts. These were hand-curated, but there's a lot of other ways you could try to do automatic prompt optimization. And they said to people, I want you to imagine you're thinking like a zero-level thinker, et cetera. And so baseline AI is very poor. That was the take caution result. And their optimized mixture was much better. So the humans are these black bars, and the AI predictions are in kind of light blue, and they're a little bit off on the humans, but they're a lot closer with steering. So the takeaway from this is, if you write a paper in June that says take caution, LLMs don't work, someone may write a paper less than 3 months later that says we can make them work. So that's why I'm so optimistic about AI for social science. It's the cycle time. Right, something that in 2025, in June, was essentially falsified, or at least the oomph of the paper was immediately falsified in 3 months. That's progress. Okay. I think I need to finish up, so let me just do one last thing. I'm going to skip over labor markets, even though there's a lot to say about that. Damn it. Okay. All right, let me say one thing about labor markets. Let's start with a quote that's fun to read. 2 quotes. Is AI going to help or hurt workers? Well, it may depend who you are. Ben Mann, the co-founder of Anthropic, said $100 million for a 4-year package. That was supposedly the numbers that Meta was offering to people from OpenAI and thinking machines, is actually pretty cheap because they can add a lot more value. Kate Smahe, who's the head of tech at McKinsey, says, do we need armies of business analysts creating PowerPoints? No, the technology could do that. And actually, these 2 quotes are kind of exemplified by 2 things you see in the data, or certainly one thing. So this is a case study of some companies that have customer service reps. And this is the head count, the number of jobs of customer service reps before and after AI was introduced in this company. And what you can see is the blue line and the orange are people 22 to 30, they shrink, they're losing jobs. But the others are increasing, right? So AI kills these jobs for younger people. At the same time, this is a different study. If you look at the productivity impact on AI, that's the y-axis, for people with different amounts of experience when they're first starting. For people who are first starting out, the first 0 to 6 months they're at the firm, AI is boosting productivity a lot, right? But it only works so far. Okay. And so there's a new paper by Gattacano and Rayo, which I cited earlier, or I gave you this citation, was on the slide earlier. And they point out that from a labor economics point of view, AI rather has two effects. One is if it substitutes for low-skilled workers, it's going to create unemployment. That's what you saw on the graph. The 30-year-olds and under are out of a job. At the same time, if you're a surgeon or a radiologist or a managing partner or a PI in a science lab, AI as a co-pilot may exhibit what we call complementarity or synergies, which means a better AI will make you a much better scientist. And they write down a little model meant to apply to things like law, management consulting, maybe science, in which apprenticeships are safe. That means it'll pay for McKinsey to hire people, train them, bill them out at a very high price, and then wait and see if they're good enough to become partners. Or similarly in grad school and postdoc, right? It depends upon the ratio of the value of an AI-assisted expert to the value of AI alone. So think about a law firm, right? If you can hire AI to just review contracts and check I's and dot T's, you may not want to hire associates and pay them $185,000 a year anymore. But if the managing partner can benefit from AI so much that they can bring in lots more business or win more cases. And this magic number is E. Underneath the hood, there's a lot going on, right? But this number E means the AI has to really enhance productivity at the top of the company compared to how much it wipes out the bottom of the company. If that number is too low, we won't see any McKinsey hiring any associates anymore. It just won't happen. Okay. Finally, the last part with Tom, who's here, and Antonia Rankel. This is human-AI interaction. So there are many, many aspects of human-AI interaction, of course, trust in algorithms, et cetera. I'm just going to talk about whether we can tell the difference between AI and human faces. So we collected a data set of AI and human faces. There's a lot of technical details. Tom will talk your ear off about this if you want to know. This paper is in prep. It's not quite circulatable. And so what we're going to do is, in brain science, we often say, you could ask the people, which is explicit, like, is this AI or real? That's what we're going to do. Or you can ask the brain, or you can do both. So we're going to ask the brain and ask the people. And we want to see, can the brain data improve on human prediction of AI deepfake detection? Okay, so the subjects see a couple of hundred of these, and they just press a button if it's AI or real. Who thinks AI? Who thinks real? This one was easy. You happen to be right about this one? So we have two data sets. In one data set, the pretest effects are 50-50. People really cannot tell. And in another data set, it's a little easier. There's 70-30. Okay. And so these are areas of the brain that are differentially active when they see the real face relative to when they see an AI face. And you can see there's a few areas. This is not a neuroscience conference, so I won't go into detail, but there's areas like parahippocampus, constructing in memory, and the blue here indicates there's more activity in response to AI. The orange is more activity in response to real. So the brain's working a little harder in a way when they see AI images, which is interesting. But remember, we want to try to do predictions, so if we use principal components to dimension reduce all this brain activity, it turns out we can, the human baseline is 62.5%. Right? So they're a little better than chance because some of them are easy and some of them are not. And if we use the brain data, we can predict it around 73%. So we can do a little bit better. This is under review, and it may be, if I give this talk in the future, or Tom does, that the numbers would change a little bit. But there's some promise that in their brain, we can see whether they're detecting real or AI, even if we can add prediction power to what they tell us. And this kind of neuroforecasting or neuroanalysis has been shown in lots of other domains. Okay, recap. As a co-scientist, we can predict some social science outcomes. We cannot predict price bubbles yet. That is, the LMs do not produce human-like behavior. I mentioned human-AI interaction, and the reason I'm optimistic again is because the cycle time of improvements has been so good in a lot of domains. There's some big improvements in political science too. Eventually pollsters will not just poll humans, they'll ask an LM, if you're a 55-year-old woman in Dubuque, Iowa, who is a wife of a farmer, who would you vote for, what's your position on abortion, et cetera. I think we're going to pretty soon, meaning 0 to 3 years or 8 years, be able to do that. And the last thing is, in 2021, we published this paper in PNAS called The Golden Age of Social Sciences. And this is a nice graphic that is not AI. Actually, this was a human hired by 99 Design, but now you could probably make a better one or iterate a better one with AI. And our point was that there's so much new data across social sciences. A lot of the things we want to study, like will people take vaccines in a pandemic? They have a medical component, but also an cultural component and a political component, right, and an economic component. And so we need to put all these things together. In our paper, which is only 4 years old, the word artificial intelligence appears once. Not because we didn't think it was important, we just didn't realize it was going to be like this tsunami or jet taking off. So that's the only mistake, I think, in our paper is that we didn't say more about exactly how AI might work. But if we were writing this paper today, obviously it would be written completely differently. We'd have a lot more to say. And thanks to our wonderful funders, including the Chens.
Questions?
Yes. Hi. Hello, Professor. In one of your slides, you mentioned AI kind of is detrimental for the junior labor force, while it increases productivity for the senior labor force. So AI is good for now, but 20 years from now, what are we facing? So where are the senior labor force?
I mean, 20 years from now, 20 months from now is plenty far out. You know, so most economists, including me, even though a lot of my work is in behavioral economics and psychology, really believe in the resilience of markets and what's called the adaptation hypothesis, right? And so I think as AI gets better, people like PIs in this room or managing partners at law firms or in companies or in management consulting will learn how to use AI better and better, hopefully, or there'll be better human-AI interactions. But there may be a lot of labor force displacement. And things like, I think what will happen in management consulting is, since McKinsey and BCG and so on are so expensive, what happens is you'll have a startup consulting firm that charges a lot less. It'll be kind of like Charles Schwab or Vanguard funds that has fees of 0.08% instead of 1.5%. That charges a lot less, is very good, and then figures out how the top consultants that are senior can use AI and deliver value in a way that's going to wipe out a lot of junior consultants. There was already data yesterday, I didn't have time to put it on my slides, but companies like Accenture and Booz Allen that are now the very elite management consulting, their stock price is down by 50%. It's just going to be a totally different business.
Thanks for the talk. I love that you're using LLM for simulations. I'm shocked that more companies aren't doing that. Amazon today recently said they let go 15,000 people, upwards of 30,000. But they've doubled their headcount from 800,000 to 1.6 million pre-COVID. People talk about AI taking jobs, and I get that. Looks like ChatGPT can clearly automate customer service and routine tasks, but it still has last-mile reliability issues that stop execs from really cutting headcount. So how much of this is truly AI versus just a correction from the overhiring cycle during the 2010s?
Man, I mean, you read their press release or get on a earnings call and see what they have to say, right? I think some of it is, there have been waves of unemployment when firms like Google and may have overhired, and so I think there's some of that. There's going to be a kind of ebb and flow, like a business cycle, we call it. And some of it really is just realizing we don't need low-level software engineers anymore because the coding is so extremely good.
Right, because I remember I came out of college as a millennial, and when the great financial crisis happened, people were saying, oh, the reason why millennials don't have jobs is because of outsourcing and technology. And typically in these cycles, when you're going through layoffs, the first thing you do is you get rid of the noobs, because you're people who are experienced and can get things done.
Yeah.
You need them more, you want to hold on to them. I worked at Google when they were doing, for 2010s, I did 150 acquisitions, and so we went through a huge overhiring process. So for me, it's like I'm very bullish on the AI aspect, but I'm trying to figure out, like, what's the hype, and then where is this really properly deployed? But anyways, excellent presentation. Thank you for your time.
Thank you. Last question.
Okay. Is this working? Perfect. Then thank you very much for the great overview. I'm over here. Hi. I wanted to ask, what's your take on the current state of using AI agents as in virtual replacements for participants? Because you showed that sometimes it's working, sometimes we have to steer the models to really exhibit the human behavior we'd expect. Isn't it like we're kind of point-wise overfitting these models? Do we really have a value in using these LLM agents when we always have to steer them, fine-tune them, do prompt engineering to make them really work like humans?
Yeah, I think so. I mean, this is a wild speculation, but since you asked the question, I'll give you an answer. But I think what will happen is scientists like me across to law firms, like my wife is an intellectual property attorney, so she talks to scientists about patents all the time. What will happen in our lives and our son's life, he's 19, will be that I'll spend a lot more time figuring out how to do good prompt engineering rather than figuring out how to design an experiment or how to write for a grant or something like that. I think there'll be kind of a newish skill, which is steering, and it'll be learned like other things by trial and error. Some of the LMs will build in, better steerability or better ways to do that, and I'm very optimistic about that.
Yeah, me too, actually. I'm also working on that. So I'm wondering, do you see any avenue to really improve the steerability of the models or to really get everything right? Because we might always focus on this one aspect, maybe personality traits for the experiment or like the specific behavior of the numbers game. And I think if we want to scale things up, we really need to get everything right. So what do you think?
Oh, yeah. In the bubble data, for example, what we care about is prices, but also trading volume. And it looks like there's different types of traders. There are people who sell their shares and just sit and watch. They don't know what to do. There are other people who wait until the bubble grows and they buy way too late. They do poorly. Yeah. There are other people who seem to time the bubble and sell. And so heterogeneity is something we'd like to see. So ideally, these LLMs can whatever aspects of the data we have, they should be able to reproduce all of those aspects of the data. For example, a recent paper came out, I'm sorry, I can't remember the site off the top of my head, and it basically looked at the number of tokens in LLMs in cognitive tasks and the response time of humans. And they line up really closely. So LLM response time in the form of tokens seems to be very much like human cognitive difficulty or RTs, we call them. So that's a type of data that people hadn't been looking at until this year.
Yeah.
And
fascinating.
It's a big success
thank you so much.
in one domain.
Great, thank you. Let's thank the speaker again. Thanks. The last paper for this session is LARC, Towards Human-Level Constraint Retrosynthesis Planning Through an Agentic Framework, presented by Fraser, Baker, and colleagues.
Thank you for getting me set up here, and thank you, everyone. I'm really happy to be here, really excited to share this work with you. I'm also just really excited to get to hear all of these other talks on how AI is accelerating science. In my work, I'm really looking at applying AI to accelerate drug discovery, and I'm very fortunate to have a very diverse interdisciplinary team. Of course, I have my advisor who's over here, sitting over here, Dr. Xianing. But we also work with LLM experts like Dr. Huan Sun, who's also here. And Daniel's name that you see up there, he's actually a medicinal chemist. So we're really bringing a lot of different perspectives into this. I myself am a PhD student in computer science and engineering at The Ohio State University in Columbus. And yeah, I'm just really excited to be here to share with you how we can start to use agentic AI to integrate more depth and accelerate scientific discovery, specifically in drug discovery. With that, let's get started. So in drug discovery, we often have a molecule that we want to look at more deeply. We want to synthesize it in the real world. And when a chemist encounters that problem, they need to do something called retrosynthesis planning. In this task, they're going to be looking to find a synthetic route that is a set of reactions that they can use to produce that molecule based on some based on some purchasable materials that they can find that are commercially available today. In practice, of course, medicinal chemists will do this by hand, but there are AI approaches to do this. We typically formulate it as a sort of search problem where we're iteratively expanding this graph of possible chemical reactions, possible chemical routes, and we continue doing this until we can actually find a route all the way to purchasable materials. I'm showing a very simplified version of this here to the right, where each reaction is shown in gray, and the intermediate molecules, that is those that you can't go and buy, is shown in red. But in practice, this is usually more than 2 at each level, and you can continue to go many levels deep until, like I said, eventually you find a route. And when we do this, this search, we're typically following some kind of a search algorithm that's using either a heuristic or some value function that guides it towards short routes, where the reactions that, of course, in this case, it's a predicted reactions where they are likely to occur. And this is great, but if you give these routes to chemists, they may say, oh, I don't like this route. Maybe the route is using a carcinogen, materials that can cause cancer, which of course they don't want to work with. Maybe it has a pyrophoric substance where under standard laboratory conditions, if you don't take special precautions, it may burst into flames. These sorts of things increase the risk associated with running these synthetic experiments, but by and large are not considered by the current AI approaches for retrosynthesis planning. So we're thinking, how can we integrate those sorts of real practical constraints into our search? How can we bring additional AI into this process to guide that search? And so you can imagine, if you look again at the animation on the right, you may encounter during the search some moment where you see, oh, these are maybe carcinogenic materials, for instance. And as you continue that search, there's different ways you could approach it. You could either continue and find the route you had before, have the chemist say, I don't like this, go back and plan additional routes. But that's going to require a lot of additional generations. Alternatively, we're thinking, well, what if you can get that feedback during planning so that you avoid going that direction and you instead take a different synthetic planning path? And you come up with a route that is aware of this practical constraint. And so that's what we're trying to do in LARC. LARC is an LLM-based agentic framework for retrosynthesis under constraints. It's actually the first framework of its kind where we're integrating these kinds of constraints into retrosynthesis planning. And we're using an agent as a judge to evaluate the reactions on these constraints throughout. And this evaluation is going to guide that search process. Let's take a look at this a little bit more in depth. So the overall goal of the LARC framework, of course, is to generate that synthetic route that's going to abide by those constraints that the chemist sets. But we envision this as being something where the chemist can prompt the framework, plan the synthesis of this molecule, and avoid carcinogens while you're at it. And in this case, we see that this sort of input and output is a really versatile way to set up such agentic frameworks. And so this is just really the starting point. The agentic nature of this really comes in the evaluator. So the evaluator is going to look at that constraint. It's going to look at the prompt that the user gives, and it's going to look at its available tools. And it's going to plan, how am I going to do this evaluation throughout the search? It's going to set up a consistent set of instructions at the very beginning, and then throughout the process, it's going to use that plan to evaluate reactions. This evaluation is going to involve decision-making, so it's not just choosing which tool to call, it's also figuring out how to interpret the results of that tool and score that reaction in a way that will guide the planning. And that planning, of course, is going to be done by the synthesizer in our framework. The synthesizer is going to build on top of existing unconstrained planners, leveraging all of the AI goodness that is already there. And in our case, we actually are looking at a 3-step process where we start with an exploratory Monte Carlo tree search simulation in our existing graph. So throughout the search, that graph will grow, but up to that point, you try to explore, okay, what are the different synthesis strategies we have? Then once you have a set of candidate routes, you can expand on that. You can select one using a greedy strategy that's not concerned with exploration at all. Both of these have their own heuristic, their own value function that's guiding their choice. And in both of these cases, what we can do is we can simply integrate the reaction evaluation from the evaluator directly into that. And then, of course, the expansion is what I was talking about before, how at each step, once you select a location, a molecule that still needs to be synthesized, you can't just go and buy it. We predict possible reactions, and then the process repeats. In our instantiation of LARC, like I said, we can actually think of this as a framework on how we can adapt unconstrained planners to the constrained process through agentic AI. So we're using MEA star, which is a state-of-the-art unconstrained planner. And we're equipping our evaluator with a set of tools based on the sort of safety constraints that we're considering. But I guess the key point here is this toolbox can be expanded. We could swap out the unconstrained planner. The overall framework allows us to explore this problem in a new way. And we do, I will say, we do actually look at more than one base LLM, right? So we're not tied to any specific implementation here. And now let's dig into the results, right? I've presented this framework. You probably want to know if it works. So when we're evaluating retrosynthesis routes, we first have to think, what is the task we're asking it to do? In our case, we were concerned mostly with safety risks, which, if you think about it, it's not only for the chemist running the experiments, but even if you had a machine running the experiments, you need to care also about the environmental effects, right? The risks to the equipment and the risks to the environment that these molecules that you encounter can pose. We consider three main categories. One is avoiding carcinogens, as I alluded to earlier. The other one is those pyrophoric substances. We chose these actually in consultation with Daniel, our medicinal chemist, because we asked him what would be the things you would most want to avoid in your synthesis planning. And then finally we said, well, let's make this flexible. Let's also allow him to just specify, this is a substance I don't want to work with. And so we constructed a data set based on the unconstrained planner's routes. So we ran the unconstrained planner, we observed where it violated these kinds of constraints, and we constructed a data set from that. So in this case, LARC, in order to adapt that unconstrained planner, is going to have to, in order to be successful, is going to have to satisfy those constraints by changing the behavior of the planner somehow. The evaluation criteria, though, first we need to make sure there's a route generated from LARC. We need to make sure that it's going to hit that within its iteration limit. And then we need to make sure that route is valid, that it's a connected path from the product molecule to the purchasable materials. And then if it's a valid route, then we also need to make sure that that route satisfies the constraint that we specified. When we look at this, we compared LARC to baseline LLMs. So LLMs with no tools, just ask them to do the same planning process. And of course, LARC vastly outperformed those. But we also compared LARC against a human expert, where we gave the human expert the same tools. In fact, we told him you can refer to anything except for AI methods for retrosynthesis. And we were able to see that LARC is very, very close to that human expert line. In fact, the difference between LARC Mistral, which is the instantiation with Mistral, and the human expert is on avoiding carcinogens is just one successful route. This is really exciting because already, with a relatively straightforward agentic framework, we're approaching expert level performance. But we didn't stop here. Like I said, we also wanted to look at not only can it avoid carcinogens, we looked at other task types, other constraint types. And here we see a similar trend for the pyrophoric substances and the user-specified substances. And this is showing us that LARC is a very general framework. It can extend to these other types of constraints. Keep in mind that the tools for each of these constraints are a little bit different. The interpretation and the decision-making is a little bit different. And also the chemistry behind it is different. What makes something pyrophoric versus if you just specify, I want to avoid this molecule. Those are very different kinds of comparisons that have to be made. Again, we also want to dig a little bit deeper. We're not done yet. we want to look at how long this takes, right? We're talking about AI for accelerating science. Well, can we accelerate it? So when we compare the time that LARC takes versus the human expert, at least for LARC Mistral, we see that it's performing much faster already. This is really exciting because, of course, now we can say we're using AI to accelerate the science. And we can also envision this as being something that even if it's only approaching human level performance, it's something you could try first, right? It doesn't need to necessarily already replace the human, but it can augment and accelerate their progress. The other thing we look at is the overall route length. I think I mentioned in the beginning that current AI methods tend to plan for shorter routes. We want that, of course, to minimize the cost of a synthetic route and to just overall it's just generally preferred by synthetic chemists. They don't want this very long protocol of experiments. In our case, we do observe that the human expert is actually still able to get to shorter routes on average than LARC. And this is an interesting observation because it's telling us that some of that chemical intuition that people have been mentioning in the previous talks, some of those sorts of heuristics that the humans have in their head is still maybe giving them an advantage. Maybe that's not yet fully integrated into our agentic framework. And so one thing that is kind of interesting to think about in the future is how can we bridge that gap? How can we integrate these, something like LARC with the human chemists more directly to sort of integrate all of that knowledge? We want to look, I want to show you guys, though, a case study here so that you understand that it's not, LARC isn't just generating any routes. It's actually able to, in some cases, generate very similar routes to what the human expert generates. So in this task, if you look at the product on the right, we asked the human expert, plan us a route for this product, avoid carcinogens. We gave them the list of carcinogens, we gave them all of the tools, and we asked LARC the same thing. We said, LARC, plan us a route for this product, avoid carcinogens. And independently, they both came up with a 3-step route that if you look, looks very similar. And if you're not convinced, we actually went and highlighted all of the differences in the route for you. The main difference is in step 1, the choice of the emanating reagent. So the expert chose ammonia, which is a very economical choice and a very intuitive choice. And LARC chose a different emanating reagent, which actually on further review we found was more selective and therefore still a very good option. So that's another thing that we noticed here is that there are pros and cons to both of these routes, but overall the synthetic strategy is very similar. And that's showing us that already LARC is able to sort of mimic that synthetic planning logic of the chemist. So in conclusion, LARC is the first agentic framework for constrained retrosynthesis planning. It's vastly outperforming the LLM baselines, but it's also approaching human expert level performance. And it might not be there yet, but the fact that it's already as close as it is just very encouraging to us. It's a compelling proof of concept, and I think it's a compelling proof of concept not just for constrained retrosynthesis planning, but also for how we can use agentic AI to augment our complex scientific processes, right? To integrate that into the scientific discovery that we're trying to do and to accelerate that. We're not done. I hope you didn't think we were done. We have a lot of future directions we want to try. Obviously, LARC, we tested on some very straightforward constraints. We want to make that a lot more complex. We want to vary that a lot more. We want to enhance the demand that we're putting on that decision-making component. One of the limitations that we had so far is that trying to find the right combinations to test more complex constraints in a way that is meaningful is somewhat challenging. Trying to get the right data sets to benchmark on to make sure it's a challenging benchmark is, of course, something that we need to think about. We also want to look at how we're measuring the results from our benchmark, right? We have some metrics, but there's always more that we can do. We also want to validate the synthetic routes in the lab, obviously, if we can, but obviously at the scales that we're wanting to achieve, we might not be able to do that for everything. So how to prioritize which ones make it to the lab, that's an open question. How to validate in silico, if possible, is another thing that we'd like to explore. this space of retrosynthesis really is, I think, still, there's still a lot of room for a lot of innovation here. And of course, as I mentioned before, we have human experts with some tacit knowledge that isn't in our framework yet. We want to find ways to integrate that, bring the human into the loop as well. Also, how to evaluate, how to bring the human into the evaluation in a better way, right? So those are all things we're planning. I'd like to acknowledge the NSF and the NIH and also the Chen Institute for providing funding for this, and I also, my collaborators in the Ning Lab who are helping with figures. There's some references, and before I let you go, I also want to highlight just for a minute some of the other work that's going on. So if you're excited about AI for drug discovery, my advisor, again, who's sitting in the audience, her lab and our lab is working on this in all kinds of ways. We're going from de novo drug design, which you can see in the upper left, all the way through synthesis planning, but on the way we're hitting lead optimization, we're hitting property prediction, and we're actually looking, again, thinking agentic AI, we're looking at bringing all of these together into a drug discovery agent, which I have the pleasure of being a co-first author on. It just got accepted to EMNLP. That work is also very exciting, bringing these pieces together in a way that helps automate and accelerate this discovery faster. I think in the end, we want this to accelerate drug discovery so that we get real life-changing differences out of this. So if you're interested in any of this work, please reach out to us, reach out to me, reach out to my advisor. If you want the code and data for LARC, it's up there. You can check out more of our work at the link below, and there's also a preprint on arXiv in case you're interested in the paper. Be happy to take questions, and my email's up there as well if you have more detailed discussions you want to have. Thank you.
Questions? Maybe I can ask a question,
Okay,
maybe people prepare. So I was wondering, your constraint satisfaction was not formal, it was more agentic and data generation, right? So it's not 100%, right?
Yeah. So we're looking at the problem is constrained retrosynthesis planning, right? It's only successful if it satisfies the constraint, but the way we integrated the constraint right now is soft, right? That score helps guide it towards the routes that will satisfy the constraint, but it's not a hard constraint on the search itself.
But in the future directions, is it, do you consider also to formalize the constraints and have a formal way of satisfying them when this is sensitive?
So we could make it a hard constraint. There are certainly ways we can do that. Right now we're integrating it into the value function in that sort of additive way. There are other approaches when you look at that. Another thing too, I think though, is the multi-objective optimization. Right, you're thinking about, you want to find a route and you also want to satisfy the constraint. But at some point you might have to weigh, would you rather have no route than a route that violates the constraint? Which constraints do you care most about? Those are sort of the open questions that I think make it tricky to decide whether or not you want to make this a soft constraint or a hard constraint. In this work, we opted for a softer one so that at least we're still getting results out in most cases. So, yeah.
Okay, great.
Yeah.
Thank you so much. Let's see if there are any more questions. If not, then let's thank the speaker.
Right.
Thank you.
Thank you very much.
So this is the end of this session. Congratulations again to all the winners of the best paper in this session, and enjoy the rest of the conference. Yeah.